In calculus, we use integrals to calculate the area under a curve. However, integrals are based on a concept called a Riemann sum, where we use a series of rectangles or trapezoids to estimate the area under a curve. In the previous video, I explained everything you needed to know about Riemann sums graphically. I explained exactly what they are and how they work. In this video, I'm going to move on to explain how you can calculate a Riemann sum when you're given a table like this one, or even if you're simply given the function itself. However, if you have not watched the previous video where I introduced and explained the concept of a Riemann sum, this video is not going to make a lot of sense. So if you haven't watched the previous video, I'm going to throw a link up in this area over here in the corner. Go ahead and click on that. Watch the previous video before you go on. Before we move on, let's address the fact that because a Riemann sum is an estimate, it will likely either give you an overestimate, where the estimate is a little bit too much. It's bigger than the actual area under the curve. Or it will give you an underestimate, where the estimate is actually less than the area that's actually under the curve. The part that you have to memorize is that the two rectangle methods will give you an overestimate or an underestimate depending on whether the function is increasing or decreasing. You don't need to memorize which will give you an overestimate and which will give you an underestimate, because instead you can just quickly draw a sketch. For the left rectangle approximation method, it means that the left side of a rectangle is going to touch the function. So from this sketch, you can easily see that this is going to be an underestimate because the area of the rectangle is less than the actual area under the curve in this interval. So this particular function is increasing. So we will say that the left rectangle approximation method will give us an underestimate, and we must explain the reason. We will say because g is increasing. It's very important that you specifically name function g. Never say the function. Always say function g or function f or whatever it is. What about right rectangle approximation method? So for the right rectangle method, it is the right side of the rectangle that is going to touch the function, like this. So you can easily see that this will give you an overestimate. You can see all of this extra area that's being included that's not actually under the curve. So we have an overestimate. And the reason will be the same because the right rectangle method will always give you an overestimate when the function is increasing. For comparison, here's a function that is decreasing. If we do the left rectangle method, where the left edge touches the function, you can see that now this is going to be an overestimate. So when the function is increasing, the left rectangle method gives you an underestimate. When the function is decreasing, it's the opposite. You get an overestimate. And so if we did the right rectangle method, for the increasing graph, we got an overestimate. So you can bet that this time it's going to be an underestimate. So here we go. Right rectangle means the right edge of the rectangle is touching, and as you can see, we have an underestimate in this case. For the other two methods, the non-rectangle methods, it doesn't matter if the function is increasing or decreasing. It matters whether or not the function is concave up or concave down. So let's look at this example where the function is concave up. consider the trapezoidal sum approximation method. So let's draw a quick sketch of a trapezoid that we might consider. So for the trapezoid, we have these vertical sides, and then we connect those vertical sides to complete the trapezoid. So hopefully you can see that this is going to be an overestimate because we are capturing this extra space in here that is not actually underneath the curve. So this will be an overestimate. And for the justification, we will say because G is concave up. Whoops, that doesn't say is. Because G is concave up. Again, you don't need to memorize that the trapezoidal method will give you an overestimate in this case. Just memorize that for the TSAM and MRAM method, it's all about concavity. And then you can just draw a quick sketch. So here, for comparison, is a function that is concave down. So let's draw our trapezoid and convince ourselves what the deal is. So here are the vertical pieces, and then we connect those ends to form the trapezoid. And you can quickly remind yourself that this is an underestimate. You see the little gap there where we're not quite including all of the area under the curve. So this would be an underestimate. So don't memorize this, just memorize that it's all about concavity, and then draw a quick sketch to tell yourself whether it's an overestimate or an underestimate. I'm not going to draw a picture of the MRAM, the midpoint rectangle approximation. That will not actually convince you because it'll be a little bit over and a little bit under. So instead, I just want you to memorize that these two are opposites. So in a situation where TSAM gives you an overestimate, then MRAM will always give you an underestimate. And the reason will always be the same. For this actual example, problem number 3, is because G is concave up. So if they ever ask you if MRAM is going to give you an overestimate or an underestimate, actually just draw a sketch and do the trapezoid sketch, and then the answer will be the opposite of what you see. So now I will show you how to calculate a Riemann sum when you're given a table instead of an actual graph. For this problem, we are going to estimate the area under the curve f of x from 0 to 6. And we are told to use 3 subintervals of equal width. So if we're going to use 3 subintervals, that means we will look at intervals that go from here to here. This will be one interval. All right, I'm sort of drawing these brackets so you can picture a rectangle going through this. And then we'll have another one from here to here. So this will represent a rectangle, and we'll have a third subinterval from here to here, and I want you to picture a third rectangle as I do this. Let's start with the left rectangle approximation method. I'm going to draw a little diagram of what's going on in the first interval from 0 to 2, but you would never actually draw this. You would just picture this in your mind. So because we are doing the left rectangle approximation method, I'm focusing on the left edge of this rectangle, and that is going to touch the function. So this rectangle will be used to estimate the area under the curve for the first interval. So for our Riemann sum calculation, we need the area of this first rectangle. So base times height. So obviously the base is going to be the width of this rectangle from 0 to 2, and that's going to be 2. So that's the base. We didn't have to draw this picture. We can just see that from 0 to 2, these are separated by a width of 2. So we could find that right off of here. And in fact, let's go ahead and go through the rest of these. Well, from 2 to 4, that's also 2. From 4 to 6, that's also 2. And that makes sense because they said we needed to do 3 subintervals of equal width. So of course, the widths are all 2. Now, what about the height? We can get the height off of the table. Well, we've got 5 and 3 and 1. One of these is going to be the height of this rectangle. Because this is left rectangle approximation, the height of the rectangle is the height at 0. It's the value of the function at 0. So obviously, if you're doing left rectangle approximation, when you're looking at the table, you're going to pick the value on the left side of your interval, and that is going to be your height. So the area of this rectangle will be 2 times 5. So we can easily find the area of the other 2 rectangles without drawing any kind of picture. These are all rectangles, so it's all base times height. The base in every case is going to be 2 because all of the widths are 2. For the height, we just need to pick the left height because it's left rectangle. So this will be 2 times 1. And for the third rectangle, the width of the rectangle will be 2, and the height is going to be 7. It's the left side of the rectangle gives you the height of the rectangle. So this would be the answer for left rectangle approximation. You could just leave it like this. You're welcome to calculate it out and get a single answer if you want, but for me and for the College Board, this is perfectly fine. What about right rectangle approximation method? Well, it's going to be the same thing. We're picturing a bunch of rectangles with base and height being the area. As we already discussed, the base of each rectangle is going to be 2. So it's just a matter of what the height will be. Because this is right rectangle, now it will be the right value of the function that is the height of the rectangle. In other words, we're focusing on this position right here. So it's the value of the function at 2. So 2 times 1 will be the area of the first rectangle, and the area of the second rectangle will be 2 times 7, as we use the right value as the height of the rectangle, so 2 times 7. And then for the third rectangle, it will be 2 times 3. All we have to do is focus on the right value of the function as the height of the rectangle. And that's the answer for right rectangle approximation. So what about MRAM? What about midpoint rectangle approximation method? For this method, the height of each rectangle will be the midpoint of that rectangle. How will I find that on the chart? So for the first interval, the midpoint will be 1. So the height at that midpoint will be 3. Similarly, this will be the height of the second rectangle, and this will be the height of the third rectangle. We just have to pick the height that's in the middle. So the area of the first rectangle, remember base times height, will be 2 times 3. Plus the area of the second rectangle, base times height, again will be 2 times 3. And plus the area of the third rectangle, base times height, is 2 times 9. So that's the Riemann sum for midpoint rectangle method. Okay, what about TSAM? What about the trapezoidal sum approximation method? So we need to calculate the area of 3 trapezoids and add them together. Here's a diagram of the first trapezoid. Remember that the area of a trapezoid is given by 1/2 base 1 plus base 2 times the height. Now, these trapezoids will be sort of on their side. So this is actually base 1 over here on the left, and this is base 2 over here on the right. Where will I find base 1 and base 2 on the chart? So notice that base 1 is the height of the function at 0, or the value of the function at 0. So this is actually the length of base 1. Similarly, base 2 will be the height of the function at 2. All right, so it's going to be the value of the function on the other side of the interval. So I've got base 1 and base 2. How about the height? Because this trapezoid is turned on its side, we will be probably more comfortable thinking of this as a width instead of a height. So the height of a trapezoid is the distance between the bases. So this is actually the height of the trapezoid, but maybe we'll think of it as more of a width. So 1/2 base 1 plus base 2 times that width. So of course we already know that this width is 2. And that's going to be the same width for every single trapezoid. So now we can go ahead and set up the area of our first trapezoid by writing 1/2, okay, base 1 plus base 2. That's 5 plus 1. So 1/2, 5 plus 1 times the width, so times 2. So there's our first trapezoid. Now here comes the second trapezoid. It'll be 1/2. We need base 1 plus base 2. So in this case, we will look at these two values, all right? For this interval, base 1 and base 2, the height from the left and the height from the right. So 1 plus 7. And then again times the width. So we will have that 2. And then our third trapezoid, 1/2 base 1 plus base 2 times the width. So base 1 and base 2. Here's base 1, here's base 2. The left and the right height. Okay, so I will have 7 plus 3. And then the width again is going to be 2. So this is actually the answer, the Riemann sum using the TSAM method. And for the College Board and for me, you're welcome to leave it like this. Having said that, many people will go ahead and simplify this portion of each trapezoid because it's so easy to do. So a lot of times you'll see it written this way. So 5 plus 1 is 6, divided by 2 is 3. So this will become 3 times 2. All right, and then over here, 1 plus 7, that's 8, divided by 2 is 4. So we have 4 times 2. And then over here, 7 plus 3 is 10, divided by 2 is 5. So we have 5 times 2. So very often you will see it written this way. Let's do another example. Let's see if we can do this one more quickly without drawing a little diagram every time. Use the table below and the 4 subintervals indicated to estimate the area under the graph of f from x equals 4 to x equals 13 using left-sided, right-sided, and trapezoidal sums. So notice that these subintervals are not going to be equal width, so watch out for that. So here is the first indicated subinterval. So this is as much of a diagram as I'm going to do. And here will be our second subinterval, our third subinterval, and our fourth subinterval. So drawing this helps me picture little rectangles or trapezoids even. Okay, so left rectangle approximation method, we are going to add the area of 4 rectangles. We need base times height. So what is the width of each rectangle? You should look at the x values for that. So from 4 to 5, that is a width of 1. So these are widths that I'm putting up here. From 5 to 7, that is a width of 2. From 7 to 12, that is a width of 5. And from 12 to 13, that is a width of 1. All right, so that's the base of each rectangle. Now, what about the height? Well, this is left rectangle approximation. So f of x, these are the heights. But because we're doing left rectangle, for this interval, we will use the left height. For the second interval, well, let me alternate colors. So for this interval, we're using 2 for the height because that's on the left. For this interval, we're going to use the 6. For this interval, we're going to use the 10. So it's always the left. And for this interval, we're going to use the 8. So here we go. Base times height. So we're going to have 1 times 2 plus 2 times 6 plus 5 times 10 plus 1 times 8. And that's it for left rectangle approximation. For right rectangle approximation, the only thing that will change is instead of using the left height, we're going to now use the right height. So for the first interval, we will use the 6. For the second interval, we will use the 10. For the third interval, we will use the 8. And for the fourth interval, well, it's still an 8. So here we go. Area equals base times height 4 times. So that's going to be 1 times 6 plus 2 times 10 plus 5 times 8 plus 1 times 8. So finally, let's do trapezoidal sum approximation method. Remember that the area of each trapezoid will be 1/2 base 1 plus base 2 times the width of the trapezoid, because these are sideways trapezoids. Remember that these are the widths up here at the top. This is the width of each trapezoid. So all we need is base 1 and base 2. These will be the heights on either side of the interval. So for this first interval, this is base 1 and this is base 2. So let's go ahead and just write that one down. So our first trapezoid will have area of 1/2, okay, base 1 plus base 2, so 2 plus 6, times the width, which is 1. So that's our first trapezoid. Now, for the second trapezoid, all right, for this interval, this is base 1 and this is base 2, the height on the left and the height on the right. So here we go. 1/2, 6 plus 10, times the width, which is 2. All right, this is taking up a lot of space, but here comes the third trapezoid. So here's our third interval. This is going to be base 1. This is going to be base 2 for this interval. So we have 1/2, 10 plus 8 times the width, which is 5. All right, so I'm actually going to have to scroll over so this will fit. As we do the last interval, where this will be base 1 and this will be base 2. So we have 1/2, 8 plus 8, and then times the width, which is 1. So this is the answer. This is the expression for the approximate area under the curve as represented by a sum of trapezoids. As I mentioned in the previous problem, even though this is acceptable, many people will go ahead and simplify this part of each trapezoid. So I'm going to go ahead and do that now. So for example, 2 plus 6 is 12, divided by 2 is 6. So we have 6 times 1. 6 plus 10 is 16, divided by 2 is 8. So we have 8 times 2. 10 plus 8 is 18, divided by 2 is 9. So we have 9 times 5. And, whoa, I put an equal sign there, didn't I? Whoopsie. Anyway, 8 plus 8 is 16, divided by 2 is 8. So we have 8 times 1. So it's probably most common to see the result of TSAM written this way, because you really want to see a sum of products for your final answer. Now, in the intro, I had said that I was going to show you how to calculate a Riemann sum when you're given just a function like this, or here we have a trig one, so that's fun. But this video is already 26 minutes long, so I don't want to make this video too long. So I'm going to go ahead and make a separate video for this concept. If I think about it, I'll put a link to the next video up here in the corner.